Okay, so we just got done last week looking at derivatives of our inverse trig functions, arcsine, arccosine, arctangent, arccotangent, arcsecant, and arccosecant. So we did those derivatives. Now we're going to look at the integrals. So go ahead and have your sheets out, those charts that I gave you again. Now we're going to be focusing on the integration side of things. So we're looking at the basic integration rules instead of the basic derivative rules. And so those are the ones on the bottom. And with the inverse trig functions, we're going to be focusing on 18, 19, and 20. And so you'll notice that when we're integrating, we're not integrating a function with arcsine. We're integrating a function that's going to end up equaling something with an arcsine. So you'll notice that there isn't any rules that tell you how to integrate an arcsine, or how to integrate an arctangent, or how to integrate an arccosine, anything like that. It's what would we have to integrate to get those kind of functions as our answer. So pay attention to that. The other thing I want to point out is you may notice that there's only 3 integration rules. So there's one where you end up with arcsine as an answer, but there isn't one where you end up with arccosine as an answer. And the reason that is if you go back to the derivative rules, so let's look at 19 and 20, for example, in the derivative rules up at the top of your page, and you look at those actual rules. When you take the derivative of arcsine versus taking the derivative of an arccosine, the derivatives are actually the same. The only difference is one's positive, one's negative. So if you're trying to integrate, basically if you end up with a negative arcsine as an answer for an integration, it just means that it could be written as an arccosine. And so we don't need a separate rule for that. Same thing why we don't have an arccotangent rule. If you compare arccotangent and arctangent, and then arcsecant and arccosecant. So that's how we only have the 3 rules at the bottom that we're going to look at. And the biggest thing that I can tell you guys as we're going through these is, I've mentioned it before, the trickiest thing is trying to find the right match for these. So we've done some integration. You'll notice that all 3 of these rules have fractions. So these rules come into play only when you're dealing with fractions. But these are not the only integration rules that we have learned that deal with fractions. Natural logs. So we may have a natural log if it turns out that the top is the derivative of the bottom. So if we make the whole bottom equal to u and find our du, and it ends up being the numerator, and we get du over u, that's a natural log. We also had it sometimes where maybe we have more than just, we have something inside something else in the denominator. Maybe we can set the inside equal to u and then use our negative exponent power or properties and write it so that there is no fraction. That's also an option. So what I want to get at is don't forget those prior things that we've learned for integrating fractions. Here's just some more things to look for. So what we were going to do on these problems is we're going to try and see if we can compare it, if we can match it to one of those 3 rules. If it doesn't match out, then we can try some of the other things we've done with fractions. Try setting the inside equal to 0 or equal to your u. See what happens. Can you rewrite it using a negative exponent so you don't have any fractions? Or see if you can make the whole denominator equal to u. When you do that, does your top equal du? Then it's going to use natural logs. So don't focus so much on the new stuff that you forget the old stuff. Okay, so let's go ahead and look at just a couple of examples. All right, so looking at this first one, and looking Again, just a couple things we can try in the past. So I'm going to first address this problem as I would have in the past. So prior to this lesson, first thought would have been one of two things. I know I've got a fraction, so I'm going to want to do something with a u. I need to do some sort of rewriting. Option number one that we learned was to make the inside equal to your u. So 1 minus 4x squared equal to u. Then see what your du would be. Your du would be negative 8x dx. Okay. Now, comparing things, the problem is I don't have a negative 8x or even just an x anywhere else. And so I can't do that. So I tried it. It didn't work. Okay. So another option we had was we tried setting just the inside equal to u. That didn't work. Another thing we've done in the past is set the whole denominator equal to u. 1 minus 4x squared. Now in this case, my du is going to be quite nasty because I would have to do the chain rule. And so I'm going to end up with 1/2 1 minus 4x squared to the negative 1/2 times negative 8 over x dx. And just kind of looking at that, that du definitely doesn't match up with anything, so that's not going to work either. Okay, so our two previous skills do not work on this, which you guys probably saw that coming because we want to practice some new skills. So, but again, we still want to consider those previous skills, but now we're adding in a new option. Now, instead of using those previous skills, what I want to do is I want to look at these last three integration rules, 18, 19, and 20 on the chart. And I'm going to look at this and I'm going to see, what does this look the closest to? What does this look the closest to? And as I'm looking at this, I see three options. I see that there's a square root in the denominator. So I don't think I'm going to use 19. Both 18 and 20 have a square root in the denominator. Number 20 has a square root in the denominator and something else outside involving a variable. And in this specific example, I don't have that. Number 18 just has the square root in the denominator. One thing I do want to point out before I get too far into things, as I'm looking at these, when you're looking at these three rules, notice that the a is representing some kind of number. Okay, so the a is always a constant. The u is always representing either an x or something with x's. So keep that in mind, and that's actually true for all of the things on this chart. If they're using a, it's representing a constant, whereas u is representing, it's either a replacement for an x or it's it's something that is involving x's. So back to this problem at hand. I'm looking at this and I think it looks the closest to 18. So if that being said, for 18, the u would have to be, this term is supposed to be u squared. So the question is what would the u have to be for u squared to be 4x squared? And that's going to have to be a 2x. Okay, so make sure that you take that constant in with it. Okay, that's going to make your du a 2dx. Okay, now one thing that when we're doing the u substitution we haven't had to do before, but we are going to want to do with these rules, these inverse trig function rules, is also pay attention to what the a is going to be. this number right here is your a squared. So the a is going to equal 1. All right, now looking at this, first of all, I don't need this 3, but it's just a constant. So that's okay. So the 3 can be moved out front. All right, and then that's going to make this, so I'm moving that out front. Now I have just a 1 here when I move that 3 out in front of the integral sign. So it's not a 2, which means I'm going to want to divide by that 2 over here. So I'm going to go ahead and end up with a 3 halves out front. The 3 comes from this, the halves comes from moving that over there. Then I've got the integral of, now since it was just 1 dx, that's the same thing as my du, over the square root of 1 squared, if a is 1, then that's a squared minus u squared. Alright, so this matches up with rule number 18. So I end up with 3 halves, and then arc sine of my u, which is 2x, divided by my a, which is just 1, so just 2x. And then, as always with indefinite integrals, plus c. All right, number 2, second one here. Looking at this, and before I jump into anything, recalling some stuff from last couple chapters, I see a fraction, but in this fraction, the degree of the top is bigger than the degree of the bottom. So right off the bat, I'm going to do some division. Oops, I forgot a term in there. So I do want to put in the placeholders. Now, you may notice that this actually factors, and so simplifying this down actually ends up being easier than I'm making it, but doesn't always work out that way. So that's why I'm doing this the longer way. If you've already jumped on and caught on to how that would simplify down without doing long division, that's great, that's fine. But again, since that doesn't always work, I'm going through it the route that will always work. All right, so x squared goes into x, or x squared times what gives you x to the 4th, and that would be x squared, x to the 4th plus 0x to the 3rd, plus x squared. I'm going to go ahead and switch my signs, which is going to make that go away. 0 minus 0 is gone. And then that's going to make that negative x squared. Drop that down. And since I actually had 2 things cancel out, I'm going to drop 2 things down. X squared times what gives you negative x squared? That's a negative 1. Negative x squared minus 0x minus 1. Switch my signs. Everything cancels. And I end up without a remainder. As I mentioned, this does factor into x. It does actually factor into x squared plus 1, x squared minus 1. So things simplify down really nicely on this one. So this ends up being the same thing as just x squared minus 1 dx. So the first step, just like it was before, anytime you see that where you've got a degree on top that's bigger than the bottom, use your division to simplify it down first. Then deal with the result. Okay? If you jump into things, you might look and see you've got x squared plus 1, which if you're so focused on your integration rules for your inverse trig functions, you'll try and you may jump to number 19 as the closest option. But we were actually able to simplify this down so that our fraction is gone, completely gone. So in that case, I can just integrate this in the base using basic integration rules. So that's going to be 1/3 x to the 3rd minus x plus c. So just don't be so intense on using these inverse trig function rules that you forget the other stuff that we've done. Okay, so we're just adding tools to our toolbox. We're not throwing old ones out.